Hello again, everyone. Professor Sheikh-Jabbari, please present your book and then your talk. It's your time.
Thank you very much for the kind invitation to present my work. I would like to thank again all the organizers and the participants, especially Behnan, who has put a lot of effort in setting up these nice conferences, and I hope that it can continue and flourish in the coming years.
And see you also.
Okay, thanks. So before giving my formal seminar, I would like to present some brief note on the book that we have recently published together with Daniel Krumiller. It's a textbook, a graduate textbook on black hole physics. It's published by Springer about 2-3 months ago, and so you can find further information on the Springer website. So that's basically how the website looks. And this is the cover page, which comes with this now very famous image of the black hole. As I mentioned, it's a textbook, which means that it starts from very basics. In the book, we only assume that the reader is familiar with basics of GR, basics of Einstein equations, and then we try to build up from there. Basically, it's supposed to be a self-contained book. It has 10 chapters plus 10 appendices. In each chapter, we have a good number of exercises, and in one of the appendices, we have also given keys to the exercises. So in that sense, it's even more self-contained. So in chapter 1, we basically give the introductory review of essentials of general relativity, some different readings of statements of equivalence principle, and basically we try to give some historical review on starting from 1916 or 15, when Schwarzschild wrote his famous solution. Starting from there, we just continue on the historic line of events, both from the theoretical and from the observational viewpoints up to now. So that's basically more of like a review and introductory remarks, opening basically the topic to the readers. And then in the same chapter, we discuss different viewpoints on the basically question of black holes and how the main questions regarding black hole physics are now perceived by the community, the theoretical and observational. And we return to the same topics in the last chapter, which is the closing remarks chapter. Then in chapter 2, we basically present basics of classical solutions as black holes. We review some basic features of Schwarzschild solution, Kerr black hole, Rice-Nordstrom, and in general the Pelebonsky-Demiansky class of solutions. So we introduced very basic stuff regarding geodesics and very basic features of black holes, and Penrose diagram and the causal structure and so on. And in chapter 3, we continue on making these remarks that we have reviewed in chapter 2, and we put it in more formal way. So we present more formal definitions of what are different notions of horizon are, and classical theorems like just the famous optical theorem, focusing theorem, singularity theorems, and so on, the area theorem. We give brief overview of the proofs, but we don't provide the full proof, which we refer to the main original papers on that. And then we go on chapter 4 by studying how we can probe black holes with different probes, from particle probes to light and photosphere and those sort of things. And we also discuss stability issues and formation of black holes through collapse procedures. Chapter 5 is sort of closer to my own research, which is basically we provide a detailed discussion on the charges, different charges that one can define in GR in general. We start from the basics, the Noether theorem and so on, Komar charge, and then we ADM charge and so on. We move on to the covariant phase space method and the proof of 3 laws of black hole thermodynamics. From chapter 6 on, we basically move to semi-classical or quantum aspects of black holes. We review now the standard and classic things like Hawking radiation, en route radiation, the tunneling method, and all what comes into semi-classical description of black holes. Chapter 7 deals with black holes in diverse dimensions, 2, 3, and dimensions higher than 4. And chapter 8 and 9 are more advanced research areas. In chapter 8, we review ADS-TFT and holography. And basically, we focus the discussions on the ADS-TFT related to black hole topics. And chapter 9 is sort of less established areas of quantum aspects of black holes in string theory, fuzzball program, and so on. And we also review various recent discussions on the island conjectures. I mean, the debate on how one can resolve information problem. And we close in chapter 10. And as I mentioned, it's supposed to be self-contained book, so we have gathered all the different details of technical details in the appendices. So these are just some latest observational information on black holes which we have reviewed in the book. So this is basically the state-of-art merger of black holes or merger of neutron stars into black holes. How basically two massive objects can merge into a more massive object. So that's basically the highest mass black hole that has been observed, close to 200 solar masses. And let me just finish by a few comments. And so, as I mentioned, we have lots of exercises in each chapter, and we give keys or hints to these exercises in the one of the appendices. And while we try to be concise, we are not very detailed in special proofs of different theorems. We have given the idea of the proof and the main steps, but not all the details. In some cases, the details are left to the reader as an exercise. We have tried to be comprehensive and give up-to-date reference list so that the reader can follow up the issues that have not been discussed in detail in the main book. And we have tried to sort of have the history right, and we have tried to dig out the references and talk to people on the history of how things have evolved and established in the last 50 years or so. So this took a lot of time, basically talk to people and make sure that every detail that we quote in the history is correct and the credits are given in the right way. And while it is more about theoretical aspects, we also touch on observational features which are very timely and important, especially in the near future. So I hope you enjoy the book, and please let us know if you have any comments or you find some typos in the book so that we can improve and correct it in the hopefully next editions in the coming years. So that's for the book. I would be happy to take questions or comments if there are any.
Thank you for introducing your book. I know writing such a book needs several years hard working. Thank you to give us this book. If anyone has question, raise right hand. Dr. Nozari, do you have a question? Seems there is no question. Your microphone is active, Professor Nozari. So let me introduce the chairman of this session, Professor Izzat Sakali. Professor, your microphone and webcam is active.
Okay, thank you. Do you hear me? Behnam? Okay, thank you very much. On holography and its applications. The first one was done in the July of 2022, and as far as I see, it goes better and better since we get a good attention from the scientists in the worldwide. Now, I would like to invite one of the renowned professors of the world, who is Mohammed Mehdi Sheikh-Jabbari. He is from School of Physics, Institute for Research in Fundamental Sciences, in other words, IPM, Tehran, Iran. And I also congratulate him for his great monograph, which is entitled with the black hole physics from collapse to evaporation. He introduced very nice of his book. I am sure that it will get too much attention in the literature. The title of his talk is about the horizon strings as 3D black hole microstates. And if we have a look at its abstract, one can see that he is going to construct microstates of 3D black holes in the Hilbert space of tensionless null strings with non-zero winding along the bifurcation horizon. Counting these string states, he is going to recover the Bekenstein-Hawking entropy and its semiclassical logarithmic corrections. Now, I would like to invite the Professor Mehdi Sheikh-Jabbari to give his speech. Professor Sheikh-Jabbari, this is your turn.
Thank you very much for the time. Let me just with the main seminar. As was mentioned, I'm going to tell you about Daniel Grumiller in a recent paper on how to construct microstates of black holes. The example that we are going to focus on is about the three-dimensional BTZ black hole, but the proposal we hope is more general, as I'll try to outline, and is sort of applicable to high-dimensional, in particular four-dimensional Kerr black hole. So this is the outline. I'll basically go through some introductory remarks on black holes and the microstates and the need for searching for microstates of black holes. And then the proposal that we make is basically related to the fact that any space-time with a black hole has a horizon, and the horizon could be viewed as the boundary of a part of space-time which is available to a good class of observers. And hence this basically leads us to consider the question of gravity on spacetimes with null boundary. Then after going through this exercise basically and work out the details of the symmetry algebras in presence of a null boundary and so on, basically with this motivation I'll introduce the null strings as basically the theory which is describing the boundary degrees of freedom for the three-dimensional cases, the three-dimensional black holes. And through constructing the Hilbert space of these null strings, I construct the black hole microstates. And then, just as the first check, we do the counting of these microstates and show that it not only reproduces the Bekenstein-Hawking area law, but also crucially produces the logarithmic correction to the entropy of black hole. And I'll end with concluding remarks and the outlook. So just some introductory remarks on black holes. As you all know, black holes are typical solutions to Einstein GR or any generally covariant theory of gravity. What actually specifies a black hole is its horizon, and horizon is typically a null surface which could be viewed as the boundary of the region of the spacetime which is called a black hole. So the horizon is the outer boundary of black hole, or from the observer who is living outside the black hole, it's the inner boundary. Horizons divide spacetime into two causally disconnected regions, and things that fall through the horizon classically cannot come out. So that's sort of an intuitive picture of what the horizon is. Black holes can be in spacetime with different asymptotic regions. For example, they could be in asymptotic flat ADS or de Sitter spacetime. Typically, black holes have also a singularity which is expected to be sitting behind the horizon. Semi-classically, this picture that horizons are one-way basically surfaces is not true anymore, and that there could be some leakage out of this to the outside region. This is the famous Hawking radiation, and there have been extensive work, especially in the last 50 years or so, to study this feature, the semi-classical aspects of black holes. And the established picture is that black holes behave like thermodynamical systems, and they satisfy laws of thermodynamics. For stationary black holes, which have also a Killing horizon, there are formal proofs of the laws of thermodynamics. In particular, there is a proof that entropy of the black hole in Einstein gravity is given by the area of the horizon over 4 G Newton. There are different arguments why this entropy is the right entropy. Then there is also the notion of temperature, which is the surface gravity at the horizon, and the crucial point about this thermodynamical description of a black hole is that it is universal in the sense that all black holes which have a horizon all show the same thermodynamic behavior. And actually it has been established now that this thermodynamical behavior is nothing but the statement of or manifestation of equivalence principle at semi-classical level. But the same Hawking radiation, which has been shown that it leads to Hawking evaporation, and this brings the question about the unitarity of the process of formation and evaporation of black hole, the famous information problem. So the information problem arises in semi-classical description of black holes, and there are two different viewpoints on how the information problem should be tackled. One is that we should be able to find a resolution to the problem in the same level that it has come out, namely the semi-classical regime. The other competing idea is that information problem should only or can only be addressed within quantum gravity regime. So the semi-classical is not enough. Of course, there are many different papers and ideas and proposals on either of these viewpoints. And here I'm going to basically provide a proposal for which will hopefully lead to a resolution to information problem in the first camp, namely semi-classical regime is enough to address the information problem. So let me go on. The main idea which many people are trying to work through for resolution of black hole microstate information problem is to look for black hole microstates. It's not the only proposal, but that's basically the main idea in the market. Of course, there are many different attempts and formulations of the same idea. So the main idea is that basically the information problem in the case of black holes is nothing or no different than, conceptually different than the same issue in any thermodynamical system. That thermodynamical systems are not unitary because we are considering the thermodynamic limit. So if you go to underlying stat-mech system, and at that level, everything is unitary and the evolution is just like any standard evolution. But due to taking the thermodynamic limit, we basically find irreversibility and the non-unitarity of the evolution. And black holes are no different in that respect. So basically, then the main question which arises is what's the stat-mech system which underlies these black holes? The first problem or issue is that black holes are solutions to classical GR, and classical GR do not have or do not accommodate solutions which can feature as black hole microstates. So then people are led to the fact that if you're looking for some black hole microstate, you cannot find them through classical GR. We need to go to some different level. Okay. Here I'm going to set the proposal that we can find and identify black hole microstates within the semi-classical regime. And the main idea that I'm going to focus on is the fact that when we have a black hole, we have a space-time which has a horizon, and space-time contains regions which are not accessible to each and every observer. So that's the main idea that I'm going to try to study more closely and basically try to see whether presence of boundaries in the space-time can help with understanding or understanding the microstates and identifying them. Okay. So in particular, just to give you a historical remark, similar ideas have been around in the at least in the last 40 years or so, since early 1980s. There has been this proposal called membrane paradigm, and the main idea is that at the horizon of a black hole, as if there is a membrane sitting, and this membrane actually contains all information that you may find from a black hole if you're sitting outside, namely the mass, angular momentum, or charges of the black hole are actually distributed over this membrane. But the main problem is that this is not enough to give you the microstates. You need to sort of quantize the membrane paradigm. And what I'm going to tell you today is sort of a way to quantize this membrane paradigm. Okay, so after this long introduction, let me just go to the detail of the proposal and work through what the idea is. So consider a general spacetime in d dimensions. Spacetime manifold is M. It has a boundary partial M. This is a codimension 1 surface which cuts spacetime in two. This boundary could be a physical boundary or hypothetical. For example, it could be the wall of a room or a box that we have, or it could be a hypothetical part of the spacetime like a black hole horizon. It could be space-like, time-like, or null. It could be sitting in the asymptotic regions of the spacetime, or it could be somewhere in the middle of the spacetime. So basically the problem I'm considering is very general. The boundary could be anything, essentially, any codimension 1 surface. So consider a general theory described by the action S of phi alpha with generic fields phi alpha with the Lagrangian L. Now the point is, this phi alpha is basically describing the degrees of freedom that are moving in the bulk. But in presence of the boundary, we typically need to add some degrees of freedom which are residing at the boundary degrees of freedom. And these new degrees of freedom are not propagating into the bulk. They interact with the bulk degrees of freedom or among themselves. And these are crucial to, basically these boundary degrees of freedom are crucial to have a consistent theory which includes the boundary. So that's basically the main idea. And the main proposal is that similar ideas should also work for black holes. So to formulate this, we need to consider gravitational theories in presence of boundaries. So let's go back to the basics. Let's recall equivalence principle and how try to study how it behaves in presence of a boundary. So equivalence principle is formulated through the diffeomorphism invariance of the theory, which when you have a boundary in the space-time, a codimension 1 surface in the space-time, basically we are not free to choose our coordinates, namely the diffeomorphisms, as before, because presence of the boundary would naturally break a part of the diffeomorphisms. So the question is, how do we basically consistently formulate gravity in presence of boundaries? And the main question or the issue is that in presence of the boundary, there are a part of diffeomorphisms which are still remaining at the boundary. And some of them are non-trivial in the sense that we can associate some conserved charges to these diffeomorphisms, and we can use this to label these charges. We can use these charges to label degrees of freedom which are residing at the boundary. So that's the main theme that I'm going to formulate. Okay, so just to start, let's recall Einstein GR. I'll be focusing on Einstein gravity throughout, but all what I'm telling you is also true for any modified theory of gravity as well. It's enough to have diffeomorphism invariance. But just to keep the discussion simple, let's consider Einstein gravity. Recall that in Einstein gravity we have Einstein equations, G mu nu equals 8 pi G times T mu nu. And here we have D times D plus 1 over 2 number of equations. The dynamical field of the theory is the metric, which has the same number of components, D times D plus 1 over 2. Out of this, D times minus D times D minus 3 over 2 propagating gravitons, and then there are D diffeomorphisms. Similarly, in the equations of motion, D times D minus 3 over 2 are second order differential equations. These are the dynamical equations, and there are D number of equations which are first order time derivatives. So these are D constraints which can come up through Bianchi identity. Now the point is, in presence of a boundary, a part of these diffeomorphisms or a part of these deconstraints that we have actually lead to dynamical boundary degrees of freedom. They are not propagating the default, but they could be used to identify degrees of freedom which should be residing at the boundary to reinforce the presence of the boundary and equivalence principle at the same time. So a simple counting that I just showed tells us that in presence of the boundary in d dimensions, there should be, in the most general case, 2D functions over the boundary, which labels the boundary degrees of freedom. But this is the most general one. Typically, when we have a boundary, we impose extra conditions and we reduce this boundary phase space or boundary part of the solution space from this maximal 2D to some lower dimension one. In particular, let's now consider a boundary which is a null surface. That's basically what's most relevant to the question of black holes. So let me just briefly tell you what the null boundary is and how it could be related to black hole horizons. For example, recall the Schwarzschild solution. We have, this is the Penrose diagram of this Schwarzschild solution. We have this dashed lines, H plus and H cross. These are the horizons. The blue part is the part of the spacetime which is accessible to the observer outside the horizon. And this is where I'm interested in formulating my theory in physics, basically from the observer who is sitting outside the black hole. The red region is what is the black hole region. So that's the part which is behind the horizon. So, and these lines are, the horizon are null surfaces, meaning that all the different points on this could be, on this H plus or H cross could be, H minus or H plus could be related by null rays. So this is basically, the question is how can I formulate my gravity theory from in this blue region only when I cut out the part of the space-time behind the horizon. So that's the kind of question. And the question is what do I need to add at the boundary degrees of freedom, which basically guarantees this cutting out of the part behind the horizon is consistent. So just more formally, let's consider any null surface, this n, the line 45-degree line n, which denotes basically a codimension 1 boundary, the null boundary. In the spacetime, I choose my coordinate r such that this null boundary is sitting at r equal to 0. The region behind the horizon is r less than 0, and the front region is r bigger than 0. And I'm going to excise the part of spacetime in negative r region. So the question is, what are the degrees of freedom? What's the physics that I need to add at the boundary to basically have a consistent dynamics, consistent within GR, within equivalence principle, in the r bigger or equal to 0 region. So basically, from the viewpoint of the observer, which has excised this part of the region r less than 0 region, the infalling null rays, the gravitons which are basically passing through this, are viewed as basically some null rays or gravitons which come to the boundary and dissolve at the boundary, because these observers do not see anything falling through. There is nothing behind it from this class of observers' viewpoint. So that's basically the kind of problem that I'm going to formulate. So now let me go through the equations with this setup. Consider the most general d-dimensional metric in the coordinate system, which is VR and XI. XI's are d minus 2-dimensional ones. the regions which are transverse to this plane that I've depicted here. R equal to 0 is a null surface, and in order to guarantee that R equal to 0 is a null surface, these coefficients of the metric, which are generically functions of all coordinates rb and xi, namely f, eta, and hij, and gi, should have this specific relation among them to guarantee that R equal to 0 is a null surface, meaning that the GR upper should be 0 at R equal to 0. And okay. So just to remember, the specific feature of these null surfaces is that any 2 points which are on this null surface and they have all the same xi coordinates could be related by a null ray, which are moving in this v direction. But any 2 points on this null surface which have different xi coordinates are causally disconnected. Okay, so this is a very feature of having null surfaces. So basically this means that typically if you have 2 points on this boundary, the null surface, they are not in causal contact. So that's the feature that one needs to remember about these null surfaces. And in the recent 2-3 years, there have been a lot of activities, a lot of papers on formulating physics on this kind of null surfaces. Usually they come under the title of Carolean field theory or Carolean theories. These are basically specific limits of usual relativistic theories in which the speed of light c is set to 0. So that's the opposite limit of having a Galilean theory. So Galilean theory is relativistic theories in c to infinity limit. These Carolean theories are the theories which are obtained from relativistic theories in c to 0 limit. But these are the theories which are relevant to when you have a null surface. Anyhow, let me continue with what I promised that I'll be doing. So I'm basically trying to see what are the restrictions on these functions f, eta, and hij, and gi once we impose Einstein equations perturbatively around R equal to 0. So that's basically a perturbative expansion for these functions with some unknowns. And basically that's what I'm, this is a specific parametrization which is convenient. And I'm going to impose Einstein equations and find relations between these different functions, gamma, omega, eta, curly g, curly j, and omega ij. So these are some technical remarks, some notations, but the point is I'm imposing Einstein equations. So Einstein equations are imposed perturbatively around R equal to 0. These are basically the what remains of these Einstein equations at R equal to 0. So basically this leads to the number of equations on these number of functions that I had introduced. These functions that I have in equation 2 are only functions of v and xi. The R dependence is taken out by the expansion, the Taylor expansion. Okay. The number of functions that I have is eta, gamma, omega, and so these are basically 3 scalar functions. Then there is a vector gi and another vector ji and a tensor omega ij. So these are basically the equations that we have. The degrees of freedom, and there is one scalar equation which is 3e and one vector equation which is 3c. So all in all, once we try to solve these equations, The solution space is basically obtained to be described by two scalars, omega and p, which is a combination of these scalar functions that I had, and ji, which is one vector, and out of this omega ij, I have this nij, which is a traceless symmetric tensor. So this is basically the most general number of parameters that fully describes the solution space. Okay. So among these functions, omega, p, and ji are actually, as we'll see, are boundary degrees of freedom, are describing boundary degrees of freedom. They are not propagating into the bulk. But nij and lij correspond to, which are symmetric traceless tensors, correspond to graviton modes, which can also propagate into the bulk. So n and l are hence bulk modes. Omega, p, and ji are boundary modes. So there are d number of the boundary modes, omega and p and ji. I is running from 1 to d minus 2, so there are d number of boundary modes, and the rest are d times d minus 3 are the gravitons. Okay, so far so good. But now the question I'm asking is, how can I label these boundary degrees of freedom by their corresponding charges? So in order to answer this question, let's focus on the part of diffeomorphisms which have not been yet fixed. So when I put my boundary at r equal to 0, I am basically, when I fix the coordinate system that I just showed, I'm fixing almost all of the diffeomorphisms, but there are a part of this which are a part of diffeomorphisms which is still remaining, and they are given by equation 4. These are the part of diffeomorphisms which keep r equal to 0 as a null surface, and it doesn't move the boundary. So obviously, if we have diffeomorphisms which only act at the boundary, these are those which are generated by t and yi, the boundary does not move, because this is just relabeling of the coordinates at the boundary. And on top of this, diffeomorphisms at the boundary, we have this scaling in r coordinate by this w function. So since the boundary is sitting at r equal to 0, if you scale r, it doesn't change r equal to 0. So this is another part, part of the diffeomorphisms in the bulk, which is compatible with the presence of a null boundary at r equal to 0. Okay, so one can, these are some diffeomorphisms. One can study the bracket of these diffeomorphisms and find their algebra. This is basically, as we expected, is a part of this is diffeomorphisms at the null surface, which is generated by t and y. And a part of this is what I've called y, which is nothing but scaling in r direction. Okay, so let me skip through this in the interest of time. These are some details, but the point is we can, we have a solution space, we have a symmetry which basically the symmetries which are generated by t, y, I, and w, which moves us within the solution space. So these are the symmetries in this usual sense of Noether, and one can use Noether theorem, or its more formal version, which is covariant basis space method, to associate conserved charges to these symmetries. Okay, and one can basically work out these charges and so on. So the details are not important for the current presentation. What we find is that there are charge algebras, which are, these charge algebras are nothing but diffeomorphisms at the boundary and plus the scaling in R. Now, I'd like to focus on the three-dimensional gravity case. and basically consider a black hole in these 3 dimensions and try to basically focus on the horizon, which should have the symmetries that we just worked through. But in 3 dimensions, the boundary, the horizon is 1 plus 1 dimensional. It's 2 dimensional. And now we want to search for a theory which resides at the boundary, and I mean the theory which governs the boundary degrees of freedom. This theory, whatever it is, should exhibit the symmetries that I just discussed. So the question is, what's the theory which resides at the boundary, the horizon of a 3D black hole here, and exhibits this d plus y symmetry? For those of you who are familiar with the string theory, that's basically what string theory is. So string theory, the worksheet theory of strings, is the most general theory, the most general 2D gravity theory, which is while plus diff invariant. So that's by definition what string theory is. But the only difference, and the crucial difference here, is that the worksheet of the string is supposedly residing at the horizon and is hence a null surface. Namely, we are dealing with a null string theory. So null strings are a specific form of strings which sort of have some specific features which are not shared by the usual tensile string theory. Let me take you through this very briefly. A null string theory, which could be obtained as a tension limit of usual string theory, is governed by this action. It's a 2D theory which has this d plus the y symmetry that I just showed. For those of you who are familiar with string theory, the difference here compared to the usual string theory is that instead of the worksheet metric, which we typically denoted by HAB, we have these vectors VA, and this is what remains of the worksheet metric in the null limit. So that's how it is different than the usual string theory. We have this kappa A, which is basically a scale of the theory. You can think it as some specific lengths, string lengths. In our case, we are the target space, which is described by metric G mu nu, is 3-dimensional, and we take it to be the near horizon geometry of a typical 3D black hole. So it has an x plus, x minus, and phi direction. Phi is 2 pi periodic, and the only thing which is remaining of a black hole in this near horizon region is the horizon radius, RH. Okay, now the rest is just easy algebra. One can work out equations of motion for this theory, for this metric, and write out the solutions which are compatible with the periodicity of phi direction. In particular, we'll be interested in closed strings, which are defined by these 2 equations here. And these are the equations of motion which we can solve, and these are the 2 constraints, equation 9. These are sort of equivalent of Virasoro constraints in the usual tensile strings. These equations are very easy to solve. This is the most general solution with this mode expansion. Compared to the usual string theory, here we don't have any sigma tau dependence. The tau dependence is not in the exponent, and it's just linear function here. So that's the most general solution for the null string. And since the phi direction is compact, we can have winding modes. A naught is the winding mode along the phi direction, and since the phi is again compact, the momentum mode along the phi direction is also quantized. We denote this momentum mode by n, or n over RH. The constraints that we deal with here, the equivalent of the Virasoro constraints, are actually forming a not a Virasor algebra, but for the null strings we have a BMS3 algebra, which is generated by this L, M, and NN. So we need to make sure that on the Hilbert, physical Hilbert space, this L and M vanish. So the rest is just standard string theory. We need to go through canonical quantization, for example. This A and B modes form a harmonic oscillator algebra, and we impose the constraints as on all physical states, Lm and Nm should be 0, and just the rest is simple algebra. There is a technical detail which is also physically important, that there are 3 choices for the vacuum state which satisfies these constraints. But for our case, actually, we choose the so-called oscillator vacuum, which is basically the one which is compatible with the light-cone gauge fixing, which is basically setting x plus equals to be a linear function in tau, and x minus is fixed through xy. With this choice, actually, we can now construct the null string Hilbert space. As in usual string theory, we have this creation operators in left movers and right movers, which act on a vacuum state. W is the winding number, T mu is the momentum mode. And then we have the constraints, which are basically the level matching condition, which is basically the total excitation number on the right minus the total excitation number on the left, should be n times w, the momentum times the winding. And the mass of the string state is given by this total excitation number, left plus right, plus the momentum mode, n squared. Okay. So far, so good. So I just briefly told you how one can construct the null string and its Hilbert space. Now you can ask, how is it related to black hole microstates? The proposal is that all the string states which are compatible with the horizon radius RH are constituting the black hole microstates. So that's sort of something like micro-canonical description. The only assumption that we make here is that the mass of the states which are contributing to microstates should be the same as the mass of black hole, which is basically something linear in RH. So then the rest is basically working out what are the how many excitations, string excitations, actually satisfy this relation. So we start with this level matching condition and the equation which relates the mass to excitation number, and insert this equation 15 and try to solve this. So we can solve this RH in terms of the strings excitations. That's given in equation 16, and its solutions in 2 particularly interesting regimes, capital N bigger than momentum, or the momentum mode is much bigger than excitation, is given by equation 17. Okay. Now let's basically explore which string excitations can contribute to the microstates as we defined. We work out some different sectors which we think are typical enough. One is the soft sector, which has 0 momentum in the phi direction, n equal to 0, little n. The high momentum sector, when the little n is much bigger than excitation. Generic sector, where n, little n, and w are non-zero, and the non-winding sector, w equal to 0. So these are 4 typical sectors. Okay. let me go through and construct what are the microstates in each of these typical sectors. For the subsector, we have the constraint, the level matching constraint, that the left and right movers should all both contribute to this, in the same way to the excitation number n over 2, and the radius is given, squared is given by n, and we can count how many integers, and basically what are the number of partitions of integers in an integer n into lower integers. So that's basically the standard Hardy-Ramanujan problem. And in large n leading order, it basically leads to this standard Hardy-Ramanujan formula. So this is the number of partitions that we have for the subsector. For the high momentum sector, actually we have basically the binding number should be 0. That's what the level matching tells us, and we can do the counting. Here the number of microstates is much less than the previous case, where we had different excitations adding up to this total excitation n. And the reason is that the only thing that we can have now is basically some different number of strings. It's not a single string state, it's a multi-string state. And then basically the number of strings could go up to little n. And since the excitations are not the main contributor to the partition, this is much, the contribution of this sector to the total partition function is much smaller than the previous cases. For the generic sector, we need to do the combinatorics a bit more carefully. So the left excitation and the right excitation is given by n plus this n times w over 2, or n minus n times w over 2. And now basically the number of total partitions is given by the partition of that we have for the left sector and the partition that we have for the right sector times the number of partitions of nw into a given integer L, which is given by tau L in this equation. So these are basically some standard number theoretic arguments that I skipped through. One can show that this tau L do not actually contribute to the leading order in this partition function, and what we remain with is basically we can set this tau equals to 1 and do this sum, and this sum could be performed using a steady phase approximation and leads to this equation that you can see in the bottom of page 36. Okay. But the main point is that to perform this sum in this equation, the main contribution is actually coming from L of order 1 to order n to 3 over 4. And the question one can ask is whether this m should be equal to this r as we had supposed earlier. And basically the answer is physically actually one needs to consider to allow m to have a Gaussian distribution, and basically sort of we need to allow m to have basically to vary over a range of n plus square root of n, or n minus square root of n. So that's basically what we have written here in the bottom of page 37. Once we what has happened to my slides? Can you see my slides? Let's see. I don't see my slides here on 38. So, sorry. Let me stop sharing and start sharing again. Okay, now, sorry. If you can basically allow for this m to vary over range n to order root n, basically what we get is the partition function is going like 1 over n to 3 hops times this exponent. For the non-winding sector, we can again do the same sum, the same analysis, and we end up with something of order n to 3 quarters. So the non-winding sector and the generic sector actually contribute in the same way. Now we can sum up different contributions that we had for typical sectors of the Hilbert space. Namely, we can sum up these different partition functions that we had. And what we get in total, which is an easy algebra, is basically something of this form. So we get the partition function of the null string for a background which has this horizon radius RH as a function of RH in this way. Okay, given the partition function, we can compute the entropy by taking the log of this, and what we find is this equation. So kappa, which was the string scale, the null string scale, if it is fixed the way it is written, kappa is 3 over 16 g squared. If it is fixed in this way, the first term in this equation is giving us the Bekenstein-Hawking area law. But the crucial point is that this the log part, the minus 3 hops log of r, is independent of the choice of kappa. And this is exactly the log contribution that one expects to see for a mixed ensemble. Mixed in the sense that we have zero angular momentum and fixed temperature. Fixed angular momentum, fixed temperature. So that's mixed in the sense that it's mixed between microcanonical, which is fixed in the angular momentum, and on the other sector we have fixed the temperature, which is like canonical formulation. And it is a well-known factor for these cases. The log correction should come with a factor of minus 3, which is what we get. So this is a quite non-trivial check for what we have done. So let me conclude. We have formulated the idea that black hole microstates could be described by the boundary degrees of freedom. In the case of three-dimensional black holes, this boundary is two-dimensional, and the theory which lives at this two-dimensional boundary is the Worship theory of a null string. So for 3D black hole, our proposal tells us that the black hole microstates is given by a null string, Hilbert space of null string theory, those which are summing up to the black hole mass. And why the null string theory is the relevant one, the relevant boundary theory, because that's the only theory, or that's the simplest theory, if not the only. That's the simplest theory which has the right symmetries, as we discussed, the right symmetries that the boundary theory should have, namely DP morphisms plus the wide scaling around the R direction. Typical microstates for these 3D black holes have a non-zero winding number. That's what we also found. And we could reproduce Bekenstein-Hawking area law plus the log corrections. To extend this three-dimensional example to 4 dimensions, where the boundary is a sphere rather than a circle, we need to consider membrane theory rather than strings. So we need to formulate a quantum membrane theory, a null membrane theory actually. There are some technical and algebraic details which should be worked through for null membrane theory, and that's a work in progress. That's what we are trying to do, and we hope that this higher dimensional example could be also worked out the same way that we did for non-strings. So to summarize, we had the proposal that semi-classical quantization should be enough for identifying black hole microstates, but this semi-classical quantization involves quantization of boundary degrees of freedom while the bulk modes, the gravitons in the bulk, remain classical. So this is sort of what we mean by semi-classical in this context. And the proposal is that the semi-classical boundary degrees of freedom are described by a membrane theory or a null string in three-dimensional case. Thank you for your attention.
Okay, thank you, Professor Sheikh-Jabbari. Do we have any questions to the professor? Actually, I have. I type it to the chat board. If Professor Jabbari can give an answer to that, I will be happy.
Are there and black hole microstates or the nature of
Is there any connection with those? I mean, the dark matter and dark energy, the nature.
Hello.
But I think, that's my personal opinion, that the dark energy problem is essentially related to what we have here. So here I presented this boundary degrees of freedom and so on for a black hole case, but exactly similar formulation with similar results also works for cosmological horizons. And I think that in that setup,
But I don't hear well. Could you speak close to the microphone? Yes, now it's much better. Thank you. Yes.
This is described by but by my or semiclassical gravity. So the short answer is I think it is related, but it's not the conventional view.
Thank you very much. Do we have another question? If no, I would like to thank you to Professor Sheikh-Jabbari.
Sorry, yes. Yes, there are several questions.
Ask.
Masoud, you can ask your question.
So, I don't know if
We have also a question.
Yes, please ask it to Professor Sheikh-Jabbari.
Is the octane entropy, for example, on page 41, is including quantum corrections? My mean is that is it possible to calculate non-perturbative corrections which are exponential, or it is impossible for this entropy as it is itself including quantum?
So let me reiterate the question as I understood it. So basically, here we have tried to compute the partition function, and here I've used this sign semi-equal to, and this sign stands for keeping up to log corrections to the entropy. So all the computations of the partition functions that I skipped through, so the first equation, for example, in this one, is exact. But then the second equation, we have just used the approximation, and it's only written up to the log corrections. So here in this computation, we do not keep beyond the log corrections to the entropy, which is basically the polynomial independence in the partition function. So, but in principle, the equations that we have, for example, here, for this other sector, let me show you this one, includes, so we have the full expression, but we cannot compute it explicitly beyond the leading log. So, and on top of this, we have not computed the full partition function in the sense that we have only considered 5 typical sectors, and which we know that they give the leading contribution, so to the partition function. So this expression that we have written is also sort of an approximation. This one is an approximation in the sense that we have considered contributions in the leading log order. So in principle, it is possible to do the computation, but what we have is not nothing beyond the leading log.
Thank you. I think Masoud has a question.
I hope I'm audible. Professor Jabbari, can you hear me?
Sure. Yes.
Pardon my ignorance. I'm not into strings actually very much, so I'm just a student. So I'm just struggling sometimes to understand this, a very generic question rather, which you just mentioned. I think you just slightly touched in the earlier these slides when you're talking about the asymptoty of the black holes. It can be de Sitter space, it can be anti-de Sitter space, or it can be this flat space if it's a Schwarzschild or other Kerr-Newman black holes without this dark energy. I've been always wondering, I mean, when we formulate this bulk boundary correspondence about this negative cosmological constant, what's the role of positive cosmological constant? Number one point. Pardon me for ignorance. If someone has asked this question already, so I should apologize for that, because I really don't know. I have some problems with this audio. And the second question is, what happens if we increase this dark energy component too much? What happens to this bulk boundary correspondence, especially if we reach the extremal limit of Schwarzschild or Kerr-Newman de Sitter spacetime? So please, I would like to have your view on this question.
Okay. So the first, regarding the first question, what I can add is that to work through our proposal, we are only focusing on the near horizon geometry because that's where we think the boundary degrees of freedom are resident.
Right.
And once you focus on the horizon, actually it's not physically relevant what's in the asymptotic region of the space-time.
Okay. Okay.
Okay. So this is so as far as our construction is concerned, the asymptotic region of the space-time is not relevant. But if you were asking about the general ADS-CFT type correspondence, of course it depends on whether what's the asymptotic region, right? So I can make some remarks. If you have a, for example, black hole which is very small inside an ADS geometry, this is called a small black hole. Actually, as far as the ADS-CFT is concerned, it has a sort of complicated description. The black holes which are easy to understand through ADS-CFT are those which have the horizon size of order of ADS radius. These are the large black holes. Okay, so you can find more details in the literature of ADS-CFT on this. So how the small or large black holes are described in the ADS-CFT. I don't know if this was enough for your question, but there's a long.
In particular, I was interested about the extremal geometry. If we increase lambda beyond a range that the two horizons coalesce together, what would happen to this area's boundary?
Okay. So this can happen if lambda is positive.
Yes, yes, positive lambda. Exactly, positive lambda. Yes.
Something like an area geometry will appear.
Okay.
And in the there basically the near horizon geometry is like the Sitter times sphere, right? And you can basically, I mean, the Sitter two-dimensional, the Sitter ds2 times s2. So you can basically try to, if you want to work through our proposal, you can still do it. In the near horizon geometry, you will have something like the Sitter 2 solution. But as a general remark, since you asked, in our construction, actually, we were implicitly assuming that the black hole that we are considering is not extremal, because the near horizon geometry was just a flat space in the three-dimensional case across a circle, rather than the Sitter or ADS2 across a circle. So for the extremal case, one needs to reconsider the whole problem from
Okay, thank you.
So
thank you very much.
That's
yes. Okay, let's all thanks to Professor Sheikh-Jabbari for his excellent talk. Thank you very much, Professor. I think it's time to pass to the next speaker. Professor Behnam Hassan. The next speaker will be Professor Ali.